Hello and good morning. Today we're going to be talking about the biocatalytic synthesis of the diabetic drug sitagliptin. Firstly, here is some background on the disease of diabetes and the background of the drug.
Diabetes mellitus, also known as type 2, and diabetes insipidus, also known as type 1, share the name diabetes because they are both conditions characterized by excessive urination or polyuria. Through this video, we will discuss diabetes, and by this we mean type 2 diabetes. Diabetes in general is a spectrum of diseases which manifest themselves as an inability of insulin to properly regulate glucose metabolism, either by insulin not being produced or because insulin is being produced but is unable to function properly. There are a number of drugs in use for treating type 2 diabetes that work by increasing the activity of the incretin or GLP-1 signaling system. These drugs improve beta cell function. Sitagliptin is an example of a drug in this class. Sitagliptin is a highly selective DPP-4 inhibitor, which exerts its actions in patients with type 2 diabetes by slowing the inactivation of incretin hormones. This increases the concentration and prolongs the action of these hormones. Incretin hormones, including glucagon-like peptide 1 and glucagon-dependent insulinotropic polypeptide, are released by the intestine throughout the day, and levels are increased in response to a meal. Drugs that are currently funded by Pharmac and in use in New Zealand for treating type 2 diabetes include a class of drugs called biguanides, such as metformin. This is usually the first-line treatment for diabetes in New Zealand, but it has gastric side effects and usually only works for a few years. Sitagliptin can be given in combination with metformin. Advantages of sitagliptin is that it is weight neutral and it has a low incidence of hypoglycemia.
To appreciate the biocatalytic pathway used to make sitagliptin, we will first look at the classical synthesis pathway.
The synthesis of sitagliptin has evolved over time. The first synthesis was used to develop about 100 kg of sitagliptin for early clinical studies. Unfortunately, this process was very inefficient. It involved 8 steps, produced 250 kilograms of waste for every kilogram of final product, and had an overall yield of 52%. Improvements to this method were essential for the manufacturing of sitagliptin on an industrial level. Initially, the process was improved by the removal of the waste-intensive Mitsunobu reaction, replacing the synthesis with a 3-step one-pot synthesis of dihydrositagliptin. Overall, waste was reduced to 50 kilograms per kilogram of final product, with the overall yield at 65%. Finally, the synthesis was improved using biocatalysis, decreasing waste by 19%, increasing yield by 13%, and productivity by 53%.
Now that we know the ups and downs of the classical synthesis pathway, we will look at the biocatalytic synthesis pathway.
Now you may be thinking from the biocat that this means we're going to talk about the biological makeup of very fat cats. But no, we're actually talking about biocatalytic processes which use biocatalysts that are produced from renewable resources that are biodegradable and only use non-hazardous and non-toxic chemicals. Generally, biocatalytic syntheses are performed under mild reaction conditions, which decreases the potential chance for something to go wrong. Because of these reasons, biocatalysis syntheses are more cost efficient and generate less waste than seemingly convenient existing industrial productions. This means that it is extremely environmentally attractive and sustainable while conforming to the 12 principles of green chemistry. The biocatalytic synthesis begins with prositagliptin, which undergoes ketoamide transamination. This transaminase step favours the ketone instead of taking the rhodium route to produce the sitagliptin intermediate in this previous step. It is then purified with phosphoric acid, which we know is a weak acid, and produces a higher yield and a purer final product of sitagliptin phosphate. The biocatalytic synthesis completely eliminates the use of all heavy metals, and in this particular case, the removal of rhodium, which is a chemically inert transition metal that requires carbon treatment to remove in the chemocatalytic synthesis. This is important as rhodium compounds are highly toxic and carcinogenic. The biocatalysis synthesis also reduces the total manufacturing costs, and the enzymatic reaction runs in a multi-purpose vessel, therefore eliminating the need for specialized reaction vessels.
In general, biocatalysis is a mix of pros and cons, and we will explore these concepts now.
As catalysts, they increase the rate of reaction. However, biocatalysts provide some unique characteristic over conventional catalysts. The largest benefit is high selectivity, including stereoselectivity, radioselectivity, and chemoselectivity. This results in reduced or no need for protecting groups, minimal side reactions, and easier separation. Another advantage is that biocatalysts are generally more efficient, i.e., lower concentrations of catalyst can be used compared to traditional synthesis. That being said, biocatalysts are susceptible to inhibition either by substrate saturation or that the product of the reaction inhibits the catalyst, so higher concentrations might have to be used to counteract this. Because biocatalysts are biological molecules, they can be modified to increase selectivity, affinity, stability, and activity. This can be done by genetically modifying existing biocatalysts. However, the general public get antsy when GMOs are brought up. Hopefully, this stigma changes in the future. Biocatalysts are also generally environmentally friendly as they are often sourced from nature and are made of biological components. However, some enzymes can cause allergic reactions when people or animals are exposed to them.
In conclusion, the use of biocatalysis has made the synthesis of sitagliptin infinitely better, and biocatalysts in general are changing and improving the way we conduct chemistry today. Thank you everyone for listening. We hope that you enjoyed our YouTube presentation.